Good afternoon, everybody. So I hope you are doing well. So today, who's gonna tell me what we have learned in the last class? Can you just remember anything from last class?
Uniform flow.
Yeah, exactly. We have computed the normal depth of uniform flow in the last class, right? So my today's topic is very interesting. I think it will be interesting to you as well. So it is the specific energy and the specific energy diagram, right? So before defining this specific energy diagram, we can just recall from our previous lectures that how can we calculate the total energy at a channel section, right? I'm just demonstrating here. So if this is the bottom of the channel and this is the datum, right? So if I measure all the energy at any section of the channel, so if this is the elevation here and y is the depth of water, and if I add the velocity head, so total energy at this section will be the summation of these three, g plus y plus v squared over twice g, right? So for specific energy, the equation is same, but we have to modify a little bit. So see, so definition is the energy which is measured with respect to the channel bottom. More specifically, specific energy is defined as the energy per unit weight of water measured with respect to the channel bottom. So what will happen if I assume that energy is being measured from the channel bottom? That means G will be equal to 0 and the equation becomes this way, right? E is equal to y plus v squared over twice g. So this is the equation of a specific energy. So I can represent, or I can write this equation differently. So from the last class you also know what is the continuity equation, right? Q is equal to AV. If I replace this D this way, Q over A, where A is the cross-sectional area, then what I'll get from this equation? So the equation can be written as y plus q squared over twice g times a squared, this way. So what can I understand from this equation? So this equation represents that the specific energy depends on the depth of water, right? It is also a function of discharge, and it also depends on the cross-sectional area. If the cross-section changes from rectangular to trapezoidal, the area will be changed, right? Then the specific energy will differ. So this is the equation we will use to calculate specific energy. So can you guess what we will do with this specific energy? So we are calculating this specific energy, right? So what the use or the practical application of this specific energy? We are just trying to calculate the channel sections, right? The properties of channel section, like the velocity, depth, and in the last class we computed the depth of water of a uniform flow, and then we computed what is the state of the flow, right? But what we will do with this specific energy? Yeah, we'll get the answer, and then, so let's move to the diagram, then we'll have our answer, right? So what is the diagram or curve? It's a diagram which will represent a specific energy, but the diagram is pretty interesting and is very meaningful. So the specific energy diagram is a representation of depth of water against the specific energy, right? So by this time you know this. So this is the diagram. So if I plot specific energy along the horizontal axis and depth of water along the vertical axis, right? And what I have to do So I can just draw it here this way. So if I draw a one-to-one line, that means it is a 45-degree line, and this is the specific energy curve. So Y will be along the vertical axis and E will be along the x-axis, right? So from this equation, if I use Y is equal to 0, what will be the value of specific energy? Because we have A as denominator, right? So if the cross section is like rectangular section, this is B, so A will be dy. That means inside A we have depth of water. So if this y is 0, that means the total denominator will be 0. And something divided by 0 means it is infinity. And if I add the depth of water with this infinity, the value will be also infinity. That means when the depth of water is 0, the value of E, it becomes infinity. That means here you can see from this point, the specific energy curve, it will approach to the horizontal axis asymptotically, but it will never touch this axis, right? Okay. And what will happen when the depth of water will be infinity? The specific energy E, it becomes equal to the values of depth of water, and then from this point, the upper part of the curve, it will also follow the one-to-one line that is represented by this y is equal to E, and it will also try to approach that line, but it will never touch. That means it will follow the line asymptotically. So what will happen at this location? See, at this location. So is the specific energy maximum or it is minimum at this location? It is minimum, yeah. It is minimum at this location. That means specific energy is minimum when the flow is critical. So we'll learn details about the critical flow in the next class. But what will happen after that? See, for critical flow, we have only one depth. For other cases, for this case, see, we have two depths here for the same specific energy, right? I have two depths for the same specific energy, and these depths are called alternate depths, right? Now we can answer that question that we have: what is the use of the practical application of specific energy curve or this specific energy? So for example, I want to design a canal this way. The canal has this width of the canal, right? And then it expands like this way. Or there will be different situation, right? This way, flow may occur. Or the channel bottom may change this way, right? Or it may be changed this way. So what will happen then? How can we calculate the other depths? If I know the depth of water velocity at this location by applying the energy equation or the specific energy equation, I can calculate other properties at that location. This is how we can apply for designing any water distribution system or canal by using this specific energy curve. And we know for a certain specific energy we have two depths, and if I know only one depth, I can easily find out what is the other depth. So see here, y1 is less than the critical depth. So when the depth of water is less than the critical depth, the flow will be supercritical. And when the depth is greater than critical depth, the flow will be subcritical, right? And for subcritical flow, the full number is less than 1, but the depth is greater than 1. So this is the specific energy curve, and that is the equation from which we can draw this curve, right? And that is the application of specific energy in our real world situation. And here is the details that we have already discussed here on the blackboard. Right? So in summary, so in today's class we have learned about the specific energy, its definition. Right? What is the definition? When we measure the total energy in a channel section with respect to the bottom of the channel, then we call it specific energy. And what is the diagram? When I plot the depth of water against the specific energy, I'll have a curve known as a specific energy curve. And by using this curve, I can calculate one depth from another depth. Right? So this is the end of the lecture for today. So in the next class, we will learn details about the critical flow and the properties of critical flow. So do you have any more question?
Yeah, I have a question. So why is the depth of the water?
Yeah, depth of the water in the channel.
So I didn't get an idea why when y equals 0, the energy will be
Infinity.
uh,
It is from this equation. See?
so when y equals 0 means there is no water.
So I am just drawing the curve as qualitative diagram, not the quantitative. So I am just assuming the lowest value of y. So what will happen if y is less than 0? I am not assuming that. I am assuming when y is approaches to 0 or y tends to 0.
Oh.
Then the curve will be like this. It will start from here. It will follow this curve. Right? And when the depth will be infinity, the line will be this. So for each and every depth, we have a single point of specific energy. Right? For drawing this, you have to have numerous number of specific energy or numerous number of points. Then we will get this continuous line. Since I am drawing the line as qualitative, not the quantitative, that's why I am assuming what will happen if the depth of water is 0 and what will happen when the depth of water will be infinity. I am assuming the lower limit and the upper limit.
Right,
Do you
thank
have
you.
any question?
No, I'm good.
No? You are good with this? Yeah. Very good.
Right, thank you.